Okay, looks like we have a pretty good turnout today. Looks like everybody's finished the login process. Good day, everyone, and welcome to today's webinar, Squeezing Out More Test Coverage, Bridging the Gap Between Boundary Scan and Functional Test. Yeah, my name is Alan Squigna, and I'm the Business Development Manager for Asset Intertek's ScanWorks and SourcePoint product lines. Asset is a leader in boundary scan test solutions, and in this technology webinar, we'll be demonstrating how to increase board test coverage by using some more advanced capabilities inherent in our ScanWorks JTAG technology. Before we get started, I'd like to go over a few housekeeping items so you know how to participate in today's event. Firstly, today's webinar should last approximately 40 minutes. During that time, you'll have the opportunity to submit text questions to the presenter by typing your questions into the questions pane at the bottom of the control panel. You may send in your questions at any time throughout the presentation. We'll collect these and address them during the Q&A session at the end. You'll also have the ability to participate in polling questions, which will be scattered throughout the webinar, so be prepared to participate. And on that note, you've got access to a copy of today's presentation as a download, which can be found in the handouts section of the control panel of your screen. So now, without much further ado, I'll turn the time over to our presenter, Michael Johnson. Michael serves as product manager for ScanWorks Boundary Scan Test for Asset, and he also serves as manager of Asset's application engineering organization. As our product manager, Michael is responsible for providing strategic direction to Asset's boundary scan product line, while coordinating with Asset's cross-functional teams to bring the company's goals to fruition. So over to you, Michael.
Thank you, Alan. Hello all, and thank you for attending this webinar, Squeezing Out More Test Coverage, Bridging the Gap Between Boundary Scan and Functional Test. My goal today is to leave you with ideas on how you can enhance test coverage on your PCBs by functionally testing non-boundary scan devices. These devices may be going untested on your PCBs due to lack of adequate test resources, equipment, or access. But by using ScanWorks and the component action, you can extend test coverage to these devices and identify defects earlier in the product life cycle. I'll leave time for questions at the end of the webinar, and I'll also make my contact information available should anyone have questions at a later date. For this webinar, we'll follow the agenda as displayed. Test coverage considerations are areas of concern that test engineers and manufacturers must contemplate when designing and testing their PCBs. Next, we'll discuss a proposed coverage assessment methodology and the INEMI framework. We'll also examine how we can bridge the boundary scan and functional test gap by using the ScanWorks component action to enhance our PCB coverage. Next, we'll examine the component action, its structure, and functional applications. I prepared a demonstration of a few application examples, and then I'll summarize a few key aspects of the webinar. Every PCB manufacturer would like to have 100% test coverage of their PCBs, but is this achievable? I would argue that 100% PCB test coverage is achievable with significant investment of time and money. However, in manufacturing test environments, time is money. PCB manufacturers must decide on how much of each they're willing to invest to ensure a quality product. So PCB manufacturers must decide what percentage of PCB rejects and returns are acceptable due to reduced or untested areas of the PCB. And each PCB manufacturer must decide what determines maximum test coverage for their product. When asked, engineers say the goal of a PCB test plan is 100% test coverage. This is mostly achieved as an iterative process. While test coverage is an iterative process, as I just said, this is This is improved with each turn or redesign of the PCB. However, to do that, you have to follow DFT guidelines. These DFT guidelines ensure maximal layout and test coverage capabilities during manufacturing, and it guarantees us maximal test coverage on the back end of the product. As I mentioned earlier, time and money are the two factors that must be considered when devising a test strategy for a PCB. Of the two factors, cost considerations are the restricting factor. If we put too much money into a test, the coverage could be low, and that could result in warranty returns and a high cost of product replacements in the field. If we put too much money into the test, the coverage could be high and the product could become inexpensive, and that could affect the product's costs, driving up price and making it uncompetitive in the marketplace. Therefore, the goal becomes achieving optimal test coverage, that is the best test coverage achievable, given those restraining factors. The International Electronics Manufacturing Initiative, or INEMI, proposes this framework as a scientific approach to characterizing PCB test coverage. Initially, characterization of structural defects were only considered using PCOLA, SOQ, which each letter pertaining to a specific characteristic of structural tests. Later, functional characterization was added for consideration with the introduction of FAM. Applying PCOLA, SOQ, FAM provides a way of deterministically expressing fault detection capabilities of a test methodology on a given board design. As you can see, boundary scan is featured as a test methodology for testing structural devices and structural connections. Examining functional connections, boundary scan is not mentioned. So can boundary scan be used to satisfy the FAM and implement functional tests to enhance test coverage? By using the ScanWorks component action, it can. So Alan, I think this is a good time for me to pause, and I'll hand it over to you for a polling question.
All right, thanks, Michael. Will do. Let me launch this up here. All right, our first polling question is, do you use the PCOLA SOQ FAM framework to measure test coverage? And this is a yes or no question for the audience. So if y'all would please weigh in, and we'll collect the responses. So let's give it a minute. Looks like about half of the audience has voted already, up to 75%, 73%, I should say. All right. Looks like about 3/4 of the audience has participated. So I'm going to close the poll and share the results, Michael, here for a second. Yeah, it looks like 69% of the audience said yes, they do use the INEMI framework, and 31%, about a third, said no. All right, back to you, Michael.
All right, thanks, Alan. Interesting results there. PCB functional test coverage can be realized by using boundary scan, but how? The ScanWorks component action can bridge the gap between boundary scan and functional test to enhance our PCB coverage, and again, to drive our test coverage higher to that 100% goal. What is the ScanWorks component action? The ScanWorks component action is a general purpose action that extends functional test coverage to a wide array of non-boundary scan devices, such as A to D and D to A converters, oscillators, clocks, and phase lock loops, LEDs, connectors, I2C devices, Ethernet PHYs, switches, and system monitors. So as you can see, the component action can be used to test a wide variety of devices which may be going untested on your PCBs. The component action uses the tool command language, TCL or Tcl programming language, along with a PCB's existing boundary scan resources to access non-boundary scan devices. Any non-boundary scan device with boundary scan access and an algorithm that can be modeled from its data sheet through Tcl is a candidate for functional testing by the component action. The Tcl interpreter is included in ScanWorks, along with the TK package, which is also included in ScanWorks for creation of dialogues and GUIs. Component models define the pins on the target device that require boundary scan access. Component models are based on the operational algorithms of the non-boundary scan device. Component models are available for download from the ScanWorks model library for use as is or as templates for model development. And with that, Alan, I think I'll pause again for another poll question.
All right, Michael, here goes. I'm going to launch the second poll. And this one looks like sort of a yes or no question. Yeah, do you have Tcl programming experience? Yes or no? And there's, I guess, a third choice for those who want to hedge a little bit and say qualified yes. So, so audience, please feel free to select one and we'll collect the responses. Okay, I see them coming in. Terrific. About 90% of the audience has voted, and I think that's it. So I'll go ahead and close the poll and share the results again. Yeah, it looks like, all right, 25% of the audience has direct Tcl experience. 1/3 says no, and there you go. So that was a worthwhile option, Michael. 42% of the audience has a little bit of Tcl programming experience. Back over to you.
All right, thanks for sharing that, Alan. So even though most of y'all may not have Tcl modeling or Tcl scripting experience, I think it'll be pretty easy for you to pick up on. So let me just bring up a picture of the model so you can see what all is involved in creating a component action script. So again, as I've mentioned, component action models or scripts are written in Tcl, and they consist of procedures or what we call proc statements. The model is broken up into 3 sections. The proc component action support procedure loads all of the necessary asset component action classes when the action is run. Pins on the target non-boundary scan device to be functionally tested are listed in the proc build procedure. This information is used with the UUT netlist to find access to the target non-boundary scan device. The proc run procedure defines the algorithm necessary to functionally test the target non-boundary scan device. It uses the buses defined in the proc build and the user supplied commands to communicate with the target non-boundary scan device. Along with the commands you may issue in Tcl, Asset has created a set of built-in commands for use with your component models. So we have a command called set bus. There's a command called disable bus. There's a command called drscan, and there's a command called read bus. Now I won't go over each one of these commands and what they actually do, because we have a document that is in the ScanWorks install. So for those of you that have ScanWorks installed, you can navigate to C ScanWorks and the doc directory and see a document named using component actions, and it has the information on these commands and many, many more. And it also gives you some example scripts on, or that you can use as templates for beginning your scripts as well. So I would advise you to take a look at that document, because again, it does give you a lot more information on the component action and component scripts. So let's take a look at a few examples of how the component action can be used for functionally testing a PCB. So the first test we'll look at is a test where we could verify the function of LEDs. So again, LEDs can be included as a PCB functional test. The proper operation of these devices can be observed by an operator or optical sensing equipment. GUIs can be created using TK, which require operator input to confirm the identity of the operator and confirm that the device is passed. So this is just one example. Another example is verifying that connectors are properly implemented on your PCBs. So opens through a opens through a connector can be tested using a component action. By placing loopback wires on individual pins of the connector, a stimulus can be driven out of one pin on the connector and captured in on another pin on the connector. If the boundary scan device has bidirectional cells, a stimulus can be driven out of the output cell and captured in on its input cell. In both scenarios, the output stimulus driven out must match the input stimulus captured in. We can also use a component action for clock verification. Clock signals can be tested with boundary scan as to whether the clock is active or not. Using a component action with the oscillator as its target, a boundary scan pin connected to the output of the oscillator clock samples the output at specific times. The component action is written to capture a specific number of signal changes or transitions from low to high or high to low within a certain number of loops. If the clock signal does not change states, the model designed can display an error message. And just for a last example, we'll look at an ADC. Now, ADCs can be found on a variety of printed circuit boards across a broad range of industries. ADCs convert a time-varying signal into a digital value. In the application pictured, the output of two temperature sensors are measured. The device temperature sensor measures the temperature near device U2. The ambient temperature sensor measures the temperature of the environment in which the PCB is placed. The component action can measure and report the temperature at both locations. Also, board voltages can be measured as well. So Alan, I'll pause again and I'll turn it over to you for another poll question.
All right, excellent, Michael. I'll launch that up. All right, so Michael gave out four examples of, four of many, I guess, examples of applications component action is suited for. Which of these examples are of interest to the audience? LED verification, loop back, clock presence, and ADC with temperature monitor. So go ahead and this is a multiple choice. Thought it was a multiple choice, a multiple answer, but let's see. The audience is weighing in. All right, looks like we got the majority of responses coming in. I'm going to close the poll in a moment. All right, and share the results here. Yeah, it looks like LED verification didn't garner any votes at all. Loop back, 42%, clock presence, 8%, and ADC with temperature monitor, 50%, Michael.
All right, thanks, Alan. Interesting results. So we will move on. So I've shown you all of these examples, but I'll go ahead and I'll proceed with a few demonstrations. Now, the demonstrations were pre-recorded to avoid any attacks by Murphy's Law. One caveat regarding GoToWebinar in these recordings, the audio from the demonstration can only be heard through your computer speakers. So if you're watching and listening to this webinar on your phone or using your computer headset, you might want to switch over and use the computer speakers. If this is not possible now, you'll be able to hear the full audio from the recording that will be made possible or available after the webinar. Another thing, as the recording starts, the audio and the video may seem a bit out of sync, but don't worry, this should resolve itself within a few seconds. And with that, I will start the demonstration. Our first two demonstrations will verify that the D3 LED is soldered correctly on our PCB and that it functions correctly, and we'll also verify that there are no opens on a couple of pins on the J4 connector. I've created each one of these component actions ahead of this webinar just to save us some time. So you see D3 LED verification, and you also see J4 connector verification component actions on the ScanWorks GUI. Before I run each of the actions, let's take a look at the script so you get a better understanding of how they're constructed, so you'll understand the outputs when the actions are actually run. We'll start with the D3 LED verification action. I'll edit the action so we can take a look at the script. So here's the D3 LED test action or script that will be run when the action is actually run. So just going over just some of the higher level areas of the script, we can see we've created what's called a vector, and we've named that vector LED, and you'll see the number 2. So this gives us access to the LED, which is what we need in order to blink the LED on and off. So you'll see that when the action is run. Also, when this action is run, you'll see a couple dialog boxes that pop up, which will allow the operator to add some input. So first we'll ask for the operator's initials or their entire name if they'd like to input that in the box. So you have a record of the operator that actually ran this test. You'll see another dialog box that will pop up that will ask the operator to watch the D3 LED on the board to make sure that it does blink. You'll also see the algorithm here. Now this is what actually blinks the LED on and off a number of times. And then at the end, the operator will have to confirm that the LED did blink, signifying with a yes or no. And you'll also see a message if the test is successful that the D3 LED is soldered and it is working. So you'll see all that when the action is run. So let's get to it. I'll run the action so you can see exactly what I've just gone over here in the component model script. So here you see the message output. The D3 LED is soldered and working correctly. D3 LED tests completed. Now I know you didn't see the actual D3 LED blink, so what I've done is I took a video of the D3 LED, which I'll actually show you. So here you can see the operator name, Michael. You also see the D3 LED is soldered and working correctly. The D3 LED test is completed. And you see in the upper right hand corner that the test passed. Next, we'll test for opens on our J4 connector. I'll edit the action so we can take a look at the script. So here's the script that we'll use to test for opens on our J4 connector. So as you can see, we've defined two vectors. We have a vector called RX, which consists of pins on the J4 connector 1 and 3. And we have a vector called TX, which consists of pins 2 and 4 on the J4 connector. So we'll transmit on pins 2 and 4, and we'll receive on pins 1 and 3. For the test, we simply set our transmit bus at certain signals, and we receive on the receive bus. And you can see the logic that we've placed in the model. In this instance, we've set our transmit to 0, 1, and so we test for the presence of a 0 and a 1 on the correct pins. We've set our bus to 1, 0, and we simply test to see if we receive those values on the proper pins. And the last test, we set the test bus to 1, 1, or the transmit bus to 1, 1, and we test for the presence of those signals. So let's run the test. So again, we're transmitting on pins 2 and 4, and we're receiving on pins 1 and 3. So we can see the value that we expect on pins 1 and 3 for the first test is 0, 0, and we received 0, 0. We transmitted 0, 1, and we received 0, 1. We transmitted 1, 0, and received 1, 0. And we transmitted 1, 1, and received 1, 1. Now I'll disconnect pin number 1 on our loop back, and let's see what type of message we get. Pin number 1, and we can see that the overall test fails. If we look at each one of the individual tests, we can see that 1 and 3, or pins 1 and 3, which are our receive pins, expected to receive 0 and 0, but the actual receive values were 1 and 0. So pin 1 failed. When we look at the second test, pins 1 and 3 expected to receive 0 and 1, but they received 1, 1. So again, pin 1 failed. With the third test, pins 1 and 3 expected to receive 1 and 0, and we actually received 1 and 0. And with the fourth test, pins 1 and 3 expected to receive 1 and 1, and they actually received 1 and 1. So this actually tells us with pin 1 disconnected, it floats in a logic high state. Pin 1 is open on the connector, or the open is simulated with the loopback wiring that I had on the connector. For our next verification test, we'll test for the presence of an onboard oscillator. For this verification test, I've switched to a printed circuit board that has an onboard oscillator, along with a switch that opens the output from the oscillator to the receiving boundary scan device. I'll edit the action so we can take a look at the script. We'll use the scan-like clock model to test for the presence of the onboard oscillator. As we've seen before, we start out our models creating a vector. This model has a vector named clock with a pin named as number 2. So this gives us access to the output of the oscillator on the board. We have the algorithm that will test for the presence of the clock. The algorithm in this case consists of a loop that checks for the presence of the clock in the low state, and another loop that tests for the presence of the clock in the high state. So basically this script is checking for the presence of the clock, it's checking for transitions from low to high and from high to low. Let's run the action and look at the results. So when we run the action, we can see that the clock was detected in the high state a number of times, and it was detected in the low state a number of times. So again, as the script looped through, it checked for the presence of the clock in the low position and in the high position. So the overall result of running the script, or running the component action, is passed. Now let's open the switch and look at the results. So running the component action, or running the script with the switch open, we can see that the clock value is always stuck at 1. So again, we've opened up the connection between the output of the oscillator to the receiving boundary scan device. So apparently, when the connection is open, the boundary scan pin that's connected to the output of the oscillator floats in the high state. So the script or the component action is not detecting any low to high or high to low transitions. Therefore, the overall result is failed. For the last demonstration, I'll use the component action to access a 6-channel analog to digital converter, or ADC. The ADC is receiving input from 2 temperature sensors on a PCB. On channel 0, a sensor is reporting the temperature of a device of interest. On channel 1, another sensor is reporting the ambient temperature of the surrounding environment. Channels 2 through 5 of the ADC are reporting the voltage output by 4 voltage supplies on the PCB. The component action script has been written to provide an analog to digital conversion with the output corresponding to a temperature on channel 0 and channel 1. For channels 2 through 5, the component action script reports the voltages through an analog to digital conversion with the output corresponding to a voltage. I'll edit the ADC underscore 6-channel component action so we can review the component action script. The model we're using is the TLV1570 underscore 6channel.tcl script. The TLV1570 is an ADC manufactured by Texas Instruments, and the model was created from its datasheet. As we've seen in past models that we've reviewed in this webinar, the proc build consists of vector statements along with the pin numbers. We have a 4-pin bus which serves as a SPI interface to the ADC. The model consists of several procs which perform necessary functions to access the ADC and convert analog values to digital values. The bin2hex proc converts binary values to hexadecimal values. These values are used to transfer configuration settings to the ADC. The hex2bin proc converts hexadecimal configuration settings to binary to transfer to the ADC. The bits2int proc converts the bit stream from the ADC into an integer. The integer can be converted to a temperature or a voltage depending upon which channel we are reading. The proc transfer word uses the hex2bin proc to transfer binary data to the ADC and generates the bit stream that is converted to an integer. The proc SPI init bus initiates the SPI bus. Within the proc run, we set our upper and lower limits for measuring temperatures on channel 0 and channel 1 and the voltages on channels 2 through 5. The algorithm for channel 0, the sensor monitoring the temperature of the device, outputs a voltage to the ADC. The ADC converts that analog signal into a digital bit stream, which is translated into a temperature. The temperature is reported as being within a prescribed limit or out of limit. The same algorithm is applied for channel 1. The sensor monitoring the ambient temperature outputs a voltage to the ADC. The ADC converts that analog signal into a digital bit stream, which is translated into a temperature. The temperature is reported as being within a prescribed limit or out of limit by the script. The algorithm that is applied to channel 2 measures the voltage input from an onboard power supply. The ADC converts the analog signal into a digital bit stream, which is translated into a voltage. The voltage level is reported as being within a prescribed limit or out of limit by the script. The algorithm is the same for channels 3 through 5. Let's run the action and see the results. The temperature of the device on the PCB is 26.52944 degrees Celsius, while the ambient temperature is 25.49808 degrees Celsius. Both temperatures are within the limits set in the component model script. We can also see that the voltages from the onboard power supplies are within the limits set in the component model script as well. The overall result of the action is passed. I'll run the action a few more times. We can see the device and ambient temperatures increase with the time the PCB is powered on, while the voltage output of the 4 power supplies remains steady. All right, hopefully everyone enjoyed that demonstration of the 4 examples that I presented in the presentation. And so we'll proceed on. So in summary, bridging the boundary scan and functional test gap with the component action has many positive results. It adds functional testing to areas of the PCB that might have gone untested. You can implement a component action in your existing boundary scan test, so now you have one station for structural testing, programming, and also functional testing. This reduces PCB handling, and it also reduces manufacturing costs. And it also reduces the need for large equipment, saving factory floor space. Failing devices can be identified during manufacturing, where the cost to repair is lower as compared to latter production phases or at product release. Functional tests can be implemented through third-party applications such as LabVIEW, TestStand, again, along with your boundary scan tests. And Asset provides a library of component models for use as is, or you can use them as templates for your own model development. So it's very easy to get started. For more information, you can look at these links that we posted, and don't worry, you don't have to write them down now. They are included in the handout that you can download, but these are just more links where you can get information on some of our other technology offerings. And with that, I'd like to thank you for your time and attention. And Alan, are there any questions from our audience that we can answer in the next few minutes that we have available?
Yeah, there sure are, Michael. Very, very good. Let's see. As a reminder for everyone too, all right, if there's any burning questions that you haven't already entered into the questions pane, feel free to do so. But our first question, Michael, is you say that component action provides a level of functional testing capability. Does that mean it is running at board speeds?
Okay, that's a great question, Alan. Since we are using the existing boundary scan infrastructure, we're actually running at boundary scan speed or whatever you have your test clock speed set at. So we're not running at the system speed as maybe through the oscillator, the onboard oscillator, or whatever is providing the system clock for the PCB. We are running these tests at TCK or boundary scan speed, but I believe that still meets the requirement of the at speed qualification in the FAM, because it is defined as min, mid, and max of the component. So although it is not at the max speed, which would be the system speed, it is at the minimum or even the mid speed using the TCK clock. So again, not system speed from an oscillator, but through the TCK clock supplied through ScanWorks and Boundary Scan.
All right, good, Michael, thank you. Second question, can we write component action programs in a language other than Tcl?
Well, the component action is set up specifically to use the Tcl scripting language, so that the answer to that specific question would be no. However, if you're familiar with other scripting languages, such as maybe JavaScript or Visual Basic, we do have another scripting action that is basically called our scripting action within ScanWorks, where you can implement those scripting languages as well to do testing as well. But the component action is set up to use the Tcl script or Tcl language, and we chose the Tcl language for the component action because it's a universal scripting language. So engineers that do a lot of scripting that may be familiar with, again, Visual Basic or Java or other scripting languages, they generally know Tcl as well. And if they don't have any experience with Tcl, it's very easy to pick up if they have the scripting background. And even if you don't have a scripting background, it's a pretty easy language to pick up and start writing your component model scripts. And again, just as a reminder, we do supply a library of scripts that you could use as a template to get started.
All right. All right, Michael, I think we've got time for one more question, and I think you might have already partially answered this one, but it is, I know boundary scan, but I'm not a programmer. Can I use component action?
I would say the answer to that question is yes. Again, you could start out using the templates that we provide. We have models for, again, testing the clock presence, Ethernet PHYs, loopback, some of the examples that I presented during the presentation here, and even more. So we've got a library to get you started. and with a little self-study, and also with some assistance from us here at Asset, we could get you over the hurdles that you may run into in your component action script development. I think with the combination of all that, you don't need much of a programming background to get started, but again, with the resources that we provide, I think you can get started and be successful with using the component action, because again, it can certainly enhance areas of your board which may be going untested. So we're always here to help here at Asset, so we can certainly help you get started.
All right. We're 40 minutes in, Michael, so I think we're out of time for questions. Is there anything else you want to cover before we wrap up?
No, not today, Alan. Thank you. But I just want to thank everyone for attending this webinar. Feel free to contact me should you need any additional information on the component action, any other questions that may come up, in your studying of the component action and use of the component action. Again, we're always here to help. So again, thank you for attending, and I'd like to wish everyone a great day.
Good, Michael, thank you. So everyone, as you exit today's webinar, we'd appreciate it if you would complete the survey that's going to come up and provide your feedback right on the quality of our webinar today. Everyone will receive a follow-up email, within 24 hours with a link to view the recording of today's webinar. So on behalf of Asset and our presenters, my presenter, Michael Johnson, thanks very much for joining us today and have a great day.